Yes, brother, will start.
In foundation course, there are types of basically four types of vehicles. First one is this. This is soil classification. Second one are all the bearing capacities. One is calculate bearing capacity, year figure as well as settlements. The last one is the elastic settlement, settlement foundation. Start from here, calculate how to classify the soils. There are two classification. There are two types of classification. First is USDS and second is so USDS and for ASTO both require this even results. We require two types of tests if that comes in MCQ. First is we require gradation the sample or result from sieve analysis test. The second we require is plasticity and liquid limits. We have to perform the test for plastic limit and liquid limit also for this. These two types of tests are required for this, and let's start with this one. This so this is the unified soil classification chart. This one. The four basic things are in it that we have to first check whether 50% or more is retained on a C number 200 or less than 50% is retained on C number 200. If more than 50% are retained, then we have to classify the soil as gravel or sand. That I write that if retained on C number 200 are more than 50%, that 50% of the material is retained before C number 200. So our soil would be uh, sand or gravel. If there are less retained, then the soil would be silt or clay. That means the soil would be finer, and if more than 50% are retained, then the soil would be gravel and sand. First of all, let's start with soil A. Soil A, this value, this this number 200, it shows that the percentage passing in number 200 is 35. Percentage passing number 200 is 35. F200, this is F means passing 200 is 35. So how to calculate the retain one? Retain one is simple, that 100 minus F200. If you simply subtract the passing from 100, we'll get retained. So our retain will be 65, that is more than 50. So our soil will be sand or gravel. First, we have to check whether our soil is sand or gravel. So we now know that soil is sand gravel. The second step, we have to move to here. We have to check whether percentage gravels are more or percentage sand is more in our soil. That whether the gravels are more, sand is more. So for that, we classify gravels as those retained on seed number 4. Gravels are those particles that are retained on seed number 4. So if F4 is 75%, then R4 that will be retained on 4. Okay, 100 minus 75. Simply subtract the passing. These are passing percentages given. Percentage passing. Simply subtract 100. Simply subtract them from 100. So we'll get the retained one. So the retained one will be 25%. So we know that there are 25% gravels in sand. So if we write gravels, we have 25%. Fines, that means we have silt and sand as is 35%. Those passing through C number 200 are called as fine grained or silty. The sand would be simply subtract from 100 is 25 and 35. Simply we subtract from total, that is 100 is 25 and 35, we get the percentage of sand. 40 and 20, 60, 40%. We have gravel as 25%, fine particles at 35%, and sand is 40%. We can move to here. Now we know that percentage sand is more than percentage gravel. And for third part, we know that this fines are 35%, so we'll move towards here. Now we have to check which of the fines, which type of fine these are. For that, we have this A-line chart, this one, this A-line chart. So for A-line chart, we require two things, liquid limit and porosity index. Liquid limit was directly given here. Liquid limit is 21. So our liquid limit is 21. And plastic limit they have given, that was 15. Okay. So if we want to find porosity index, that is simply liquid limit minus plastic limit. So 21 minus 15, that would be 6. So we have 21 liquid limit, it would be somewhere here, and 6 plastic limit. 6 would lie between 4 and this, so our point would lie here in this hashed region. So our fine would be CLML. If we move backwards, this. So now we know our fines are CLML, this one. We are moving like this. So our soil classification for USCS, this was USCS chart. USCS, our soil classification is SCSM. SCSM. And if we want to write, and if we have to check this gravels also, so our gravel percentage was 25, we'll write this one. Greater than 15% gravel. In descriptive form, our classification would be silty clay sand with gravel. Silty clay sand with gravel. So this was simply Unified Soil Classification System or USCS classification. Any issue in this?
No problem.
All right. So the second one is H2. So this is H2 one. So for H2, first we have to find the group index. Index of our soil. So the group index formula is this one. This one. So we can write it like this, that index is equal to 0.2a plus 0.005 AC plus 0.01 PD. You have to memorize this. This one would not be given in the paper. And A is F200. The percentage fines passing sieve number 200 minus 35. B is F200 minus 15. C is liquid limit minus 40. And D is plasticity index minus 10. So the range for this A is 0 to 40. The range for B is also 0 to 40. And the ranges for C and D are 0 to 20. We cannot take any value of them less than 20, less than 0, or C and D greater than 20. We cannot take, and for A and B, we cannot take greater than 40. If a value comes, suppose negative, then simply take 0. Or if it is exceeding the upper limit, simply take the upper limit value. So we have F200 as our fines were 35%. 35 minus 35 is 0. 35 minus 15, 20. Equal limit was 21. 21. 21 minus 40 is from the negative, so simply put 0. And plasticity index was 6. Yes. So it again is.
Brother, your mic was muted.
So where did it stop, the voice?
Just that final part only, that group indexing final value. It's okay.
Fine. Or we have to calculate group index.
Yes, brother. That part is fine.
All right. So after group index, move to this chart. This. So if we write what were our values for H2, we require three values. We need to know the value passing number 10 sieve, that is 73, number 40 sieve, that is 58, and number 200, that is 35. So 73, 58, 35. 73, 58, 35. Number 10 was 73, number 40 was 58, and number 20 was 35%. So first we move to this A1 value. For A1, they are saying that we have maximum number of percentage of the soil passing number received, number 10 is 50. Maximum 50% can pass. We have 73% passing. So cross this one. We cannot take this one. Move to A1B. So A1B, we have to our soil must have maximum of 50% passing C number 40. So we have 58 greater than 40. Sorry, 50. So again cross this one. For H3 soil, we require 51% minimum passing 200, passing 40. So that's fine. And 10% are maximum fines. So we have 35% greater than 10. Cross this one also. For 8 to 4, our only requirement is 35% maximum fines. So we also have 35%, so that's fine. The again now move towards downwards. For liquid limit, we require 40 maximum. So we had, I think, 21. So that's fine.
21 years.
So and plasticity index, we require 10 maximum. We had 6. So that's okay. So our soil would be A24. For you, H2, sorry. H2, it would be simply A24, and in brackets write the group index number. Group index number must be round whole number, so you have to round it to nearest. So this is how we can write, and its its descriptive part is silty or clay, gravel, and sand. So silty or clay, gravel plus sand. So if you check this one with USCS, so it was almost saying the same thing: silty, clay, sand with gravel, and this is saying silty or clay, gravel plus sand. So this is the first type. And if the fines come, so we have to check simply. So if you quickly do the third question, third soil. So we have fines here 55%. So we can simply say that this is, you have to classify it from this chart, as our fines are exceeding 50% value. So our fines are 55%. So if for this one, to simply check the liquid limit. Our liquid limit was 21, so we'll move to the first chart. Liquid limit is less than 50. We do not have to do this in organic one, simply move towards inorganic. And now we have to check where our this is lying, sand is lying in the A line chart. So if we have its plasticity index is liquid limit is 55, 55 minus 24. So 31. I think, yes, 31. So our liquid limit is 55, and plasticity index is 34. So 34 and 55. So our soil would be lying in this portion. So we'll write this as above A line. This particular soil is lying above A line. So we'll move here. So they are saying this one, that PI is greater than 7. Yes. And our plots are lying above A line. So that's all, both are fine. So our soil classification would be CL. Soil C. Our USCS classification would be CL. And we have to check this 30 plus 200. This 30 plus means the number, the percentage retained on sieve number 200. So if we move towards here, the percentage passing on sieve number 200 was 55. So the retained percent would be 45%. So we'll check this one. This plus 200 just means that they are asking about retained, not passing. So simply this one and this one, we move towards here. That are percentage retained were 45%. So that's greater than 30%. That's okay. Now we have to check whether our sand is more or gravels are more. So simply the gravels are 5%. We can say this, that the number retained on C04 is 5% as 95% are passing. So the gravels are 5% here. The fines are, we know, at 55%. So the sand would be 40% again. So our sand is more. So this is, and we have less than 50% gravels. So our classification in the description would be sandy lean clay. All right. So this is how we have to classify. Any issue in this, or we'll move towards the bearing capacity ones?
This part is okay, brother. We'll move to that bearing capacity.
Okay, so the bearing capacity simple formula, we have to memorize this one. That this one is used always. So Q ultimate is QLT. CNCSC plus gamma DF NQ plus 0.5 gamma B and gamma S gamma. This one is the basic equation for bearing capacity. You have to memorize this one because this one would not be given in the paper. So for this one, for this equation, the C is cohesion of soil. That what is the cohesion of soil? Or if they are saying, if they have not provided C and they are saying that the soil is sand, so simply use C is equal to 0 for sands. If not provided, if they have not provided C and they are saying that the soil is sandy, so simply use C is equal to 0. NC, NQ, and N gamma. NC, NQ, and gamma. They are bearing capacity factors. So we have to memorize their values for phi is equal to 0. Phi is equal to 0. Their values are 5.7, 1.0, and 1. These values are given in this table, but for phi is equal to 0, we have to memorize them. This NQ, NC, and N gamma. Phi is equal to 0, we have to memorize. Because if they are saying that the soil is pure clay, then we have to automatically assume that phi is equal to 0. Before sand, we have to assume C is equal to 0. And if they are saying that it is pure clay, then we have to assume that phi is equal to 0 and use these values. So that's why we have to memorize them. And third thing is SC and S gamma. So SC and S gamma are shape factors. We have to memorize these values also, that for strip footing and for square footing and also circular. Strip footing, this both SC and S gamma would be 1 and 1. For circular 1.3 and 0.8. For square 1 for square 1.3 and 0.8. For circular 1.3 and 0.6. Also, a expression for rectangular is given. Also memorize this one. This one. We have to at least know these 4 values for strip and circular. Sorry, for strip and square. These 4 values. For strip, it's simply 1, 1, and for square, this is 1.3 and 0.8 because most of the questions are square footing. So these are S, C, and S gamma shape factors. Gamma, we know the unit weight of soil. df is depth of footing, p is width of footing. So we have to use these values to calculate the bearing capacities. For example, if we move to the, they're saying that a square footing, they're saying first part, a square. So for squares, simply write SC is equal to 1.3, S gamma is equal to 0.8 for square footing. And it is, they are saying that stiff clay. They are saying stiff clay and they have not provided phi value. Phi value is not provided and they're saying stiff clay. So for clay, automatically assume phi is equal to 0 degrees. And for phi is equal to 0 degrees, we have NC, NQ, and N gamma. That is 5.7, 1.0, and 0. Unconfined compressive strength of 2.4 KSF. So our UCS value, unconfined compression test, unconfined compressive strength, it is 2.4 KSF, PS per square feet. If UCS value is given, then simply the C value is UCS divided by 2. So 2.4 divided by 2, that is 1.2 KSF. If they are given UCS value, then simply divided by 2. If they are given confined compressive, unconfined shear strength. This one was unconfined compressive strength. So if they are given compressive strength, divide by 2. If they are given unconfined shear strength, simply use that as it is. So for example, they are given as Cu. This is unconfined shear strength as 1. Simply equate it as E. C. Do not change anything. So for this question, they are given compressive strength. If they are given shear strength, that added. So this is UCS value 2.4. Footing is located 4 feet below ground. So our depth of footing is, this is footing, for example. So our depth from top of the ground is df is equal to 4 feet. 4 feet below ground. And it is to carry 250 kips load. The load on footing, that is Q, is equal to 250 kips. Unit weight of clay is 125 pound per cubic feet and factor of safety is 3. Factor of safety is always 3. So unit weight is 125 PCM. FOS is equal to 3. So this is the question given. These all things are given in the question. So we have just to use, we have to simply use this equation. Q ultimate is equal to CNCSC plus gamma DF NQ plus 0.5 P N gamma S gamma into gamma. This one 0.5 gamma B and gamma. So we know the C value, UCS by 2. We know the NC value 5.7, and we know the SC value 1.3. 1.3. So C value was 1.2, 5.7 to 1.3, and gamma DF and Q. One minute. Our Q ultimate expression is, so if we are given Q ultimate, we have to find Q net ultimate. We are given Q ultimate and we have to find Q net ultimate. Value. We have to subtract Q ultimate minus gamma DF. This means net ultimate means the actual increase in pressure over the foundation. That, for example, this is our footing. This is our base. So we place this footing on this. So the actual pressure the footing is applying would be simply, we have to subtract gamma DF from Q ultimate. Why? Because we have also excavated this amount of soil. This is the depth of footing and the unit weight is gamma. So we actually have removed this much overburden pressure from the soil. gamma df. Only the footing pressure would be this one. This one is the only the footing pressure. So if we subtract q net, if we write the expression for q net ultimate, so it will be cnc sc plus gamma df nq minus 1. Just this is the difference. This was nq before, this is now nq minus 1 plus 0.5 gamma b and gamma s gamma. So if we simply write this q, we do not need to write this expression q ultimate because we'll be requiring q net ultimate, so we can simply directly write this net ultimate expression. Just the difference is this one. This is nq minus 1. Here it was simply nq. Why this is nq minus 1? Because simply we are taking this gamma df common, and in this expression this was nq, so nq minus 1 is remaining. We have taken gamma df common from this expression. So simply use this, and in this expression 1.2 into 5.7 into 1.3 and nq minus 1, because our value was of nq was also 1 and 1 is minus 1 is 0, so these both terms would be 0. The third term, because n gamma is 0, n gamma is 0, nq minus 1 is 0. Net ultimate would be simply c and csc for phi is equal to 0 choice. So after finding q net ultimate, we have to find, we have to find footing dimensions. We have to find the footing dimensions. So after finding q net ultimate, this one was q net ultimate. We have to find q net safe. So it is simply q net ultimate divided by factor of safety. 1.2, 5.7 to 1.3 divided by factor of safety is 3. That would be q net safe. Thing is q safe, that would be q net safe plus gamma df. Now we are adding the orbital pressure. So simply this expression plus 4 into whatever the gamma was. 125. 0.125. Remember, we have to make the units consistent. This C value was in KSF, kilograms per square feet. This was given in PCF, pound per cubic feet. Simply convert it into KCF, that is kilograms per cubic feet. Simply add this. This is Q safe. Now our footing dimension would be, we know that footing pressure is equal to this total load over area of footing. The total load given divided by area of footing should be equal to the Q safe, the safe fitting capacity. The area of footing would be U over QS. We know QS 250 kips, QS from here. So simply we can find area of footing. So whatever the value is, just rounded to 0.1 higher multiple. For example, if this was 6.48, this value, suppose area value comes as 101 SFT. So our V and L would be 101. That is 10 point something. So simply we can round it as 10.1 to 10.1 today. Round it to upper side, 0.1 multiples. So this is how we can find the area of footing. Any issue in this?
No, sir.
Correct. Simply first we this expression looks very large. That this is but it's simple question. All values are given. Simply we have to plug in them and find the answer. If you look to this question, they are saying that unit weight is this. We know gamma. This is C value directly given. Phi value is 30. So now we have to consult these tables for C and C for NC, SQ, and S gamma. For loop 30, we have these values of NC, NQ, and gamma. Carrying a total load, this is Q total load. Depth of footing is 5 feet. So again, the same question. Just the difference is we have changed value of NC, NQ, and N gamma. So these expression would not become 0 in this question. Here there was 0 because N gamma was 0 and NQ was 1, 1 minus 1 was 0. But in this question, this value would not be 0. Just simply some value would come and simply add it. Alright, so this one is a bit different. They're saying we have to find the load carrying capacity of this footing. So for example, this footing is given. They are saying this footing is given and its dimension 10 and 20. Simply use a smaller value for B. B is equal to 10, L is equal to 20. So the smaller one for width of footing. Depth of footing is 6 feet, Y is 35, C is 0, and unit weight is 114. Depth is 3 feet, EF Y is equal to 30 degrees, C is equal to 0, and gamma is equal to 114. PCF on depth is 6 feet. Right, so this one is given in the question, all this thing. We have to find Q, this Q load. So this is a simple question that simply just we have to first use the expression to calculate net bearing capacity. Q and U is equal to C and C S C plus gamma DF and Q plus 0.5 gamma B and gamma S gamma. So first we require C is 0, so this expression is 0 simply. We require gamma is known, so D is known, also known. DF is also known. So just we require this thing, NQ and N gamma and SC. Sorry, S gamma. So as we can
Is it not NQ minus 1?
yes, sorry. This is NQ minus 1. For net ultimate. For ultimate it is NQ, but we are going to use net ultimate always. So minus 1. Thank you. So this is, so these are 3 variables. We have these 3 variables. So simply we have to use y is equal to 30 and calculate NQ and N gamma. Simply go here and NQ and gamma from these values. This one. So 30 degrees, it's again the same values, 22.5 and 19.7. So we have NQ 22.5 and this is 19.7. The difference is S gamma because this is a rectangular footing. So our S gamma value would be a bit different. So we have to use this expression for this S gamma value. For simple circular strip or square, we simply use values. But now we have used this expression for S gamma value. Simply plug in the value B. B is we have 10, L is we have 20, 1 minus 0.2. This is 0.5, so our value will be 9.9. So this is 0.9. Simply put in the values, calculate net ultimate bearing capacity. From net ultimate, we can find net safe, that is simply Q net ultimate divided by factor of safety. Factor of safety is 3. And from net safe, we can find Q safe, that is Q net safe plus gamma dA. Simply at the overburden pressure, we can find that Q safe. And now again use the same expression. Q safe is equal to Q over A. Now we know Q A, we do not know Q. So simply Q is equal to QS into A. And we can find the allowable load or safe load from this expression. All right, so that's simply this problem. This one is also done. for this one. So for this one, they are saying strip footing. For strip footing, simply SC is equal to 1, S gamma is equal to 1 also. We have width B is equal to 3 meters. Safe load for local shear. Yes, this one is different. Local shear failure. Phi is equal to 35 degrees. C is equal to 17.25 and the gamma is 20 kilometer per meter square cube. So for local shear, there are two types of failures. The first is general shear failure. Second one is local shear failure proposed by this Targawi. Hansen or Mirov also proposed another one. They proposed this punching shear one. So simply for Tarzawi one, simply we have to use these values. We have to simply multiply by them by 2 by 3. Whatever the value C was, simply take 2/3 of it, and whatever the value of tan phi was, we have phi is equal to 30 degrees. So simply multiply 2 by 3 tan 30 degrees. Whatever the value is, simply take tan inverse of that, this value, because this tan goes there and becomes inverse. So C dash for local shear failure, 2/3 of C, and phi dash for local shear failure, 2/3 of tan phi dash. So simply this thing is different. The rest of the question is same. Just we have to change this two values. Okay. For problem 8, we have to calculate depth of footing. So this is a bit different for bearing capacity. This equation is 0 and C is equal to 0, phi is equal to 32, and gamma is equal to 17. So we have to calculate depth of footing in this expression. So our formula for bearing capacity is, just write it again and again so it is totally memorized. C and CSC plus gamma TF NQ minus 1 plus 0.5 gamma B and gamma S gamma. So for this expression, we have this unknown value. This value is unknown. Also, we are known this net safe bearing capacity. So QNS is equal to 250 kilopascals. We know this QNS is equal to Q net ultimate divided by factor of safety. In this, that Q net safe is equal to Q net allowable net ultimate divided by factor of safety. So simply net ultimate would be 250 into factor of safety. That is 3. So 750. Now simply put 750 here, 750 on left hand side. We know C is 0, I think. Yes, cohesion is 0. So cohesion is 0. So this value is this whole expression is cancelled. We know B value, and we can, so phi is given as 32. So we have to interpolate this phi value. We have to use phi for 30 degrees, phi for 35 degrees. And from these two, we have to interpolate the values of phi is equal to the value of NC, NQ, and N gamma. We do not need NC actually because we know the cohesion is 0. But for NQ and N gamma, we have to interpolate the values for phi. So we know gamma, we know this S gamma for this footing is. So they have not given this footing. So simply we can just write it as assuming footing is square footing. So simply write in, make it clear that you are assuming this value. So that's no issue, server saying. If something is not given, write into clearly that this value you are assuming. So for this, just calculate the TF value. This is the depth of footing. Any issue in this one? Problem number 9. they're saying square footing, depth is given, cohesion is given, unit weight is given, total load is given, find the width P. So that's again the same as the first question. We have to find the dimensions, the same, that's the same. Only I think the difference would be in this expression. Here in this expression, so we have to find the width of footing. So here this one would be unknown. So our net ultimate value not be a single value, but it would be something like an expression. But Q net ultimate would be something like 50,000 plus 1000 B. Because this value, this B value is an unknown. This is a variable. So we know this gamma value, we know this n gamma value, we know this s gamma value. Simply multiply them, but B we do not know. So it would be like plus something value 1000 gamma, 1000 B, sorry. And these two expression value we know, simply calculate them. So just this would be like Q net ultimate would be like this. So we can find Q net safe by divide by it by factor of safety. So if this was 9,000 and 60,000. So simply divide it by 3. So it would become 20,000 plus 3,000. Just divided by calculator. And Q net safe and Q safe would be 20,000 plus 3,000 P plus gamma DF. Just add the values of gamma DF in this one. So after this Q safe value, we know Q safe is equal to Q over A, and Q is given A is B square because it is square footing. So this becomes an expression. Suppose it's for 25,000 plus 3,000 B. Take this B there and solve this. This will become, just simply solve this using the calculators. It could become, I think, a cubic equation. So this is the difference. For this one, they are saying this concrete column 3 depth clay unit weight is this, cohesion is this, load applied is this, calculate B. Again, this the same question as the last one. Again, we have to find the B, and this like this some expression would be developed in this question also. This we are footing at depth of 3 meters below ground on sandy clay. So they in this question we have to calculate this gross safe load. So again, the same question as this one, that we have to calculate Q, and simply for strict footing we can use factor 1, and depth of footing is df is given, gamma is given, c is given, pi is given, pi is 10. Simply we can calculate the all right. Any issue in this? This is Tarzagi's bearing capacity equation. Should we move forward?
Yes, brother.
All right.
What the fuck? I'm gonna feel restricted.
Sorry. So after Tarzagi, there are 3 more equations. That is Hansen, Basic, and Mayer-Hawk. So these 3 are given. The expression is almost same. Tarzagi, our expression was we are writing for Q ultimate. So for Q ultimate, our expression was P and CSC plus gamma DF and Q ultimate, this ultimate plus 0.5 gamma B and gamma S gamma. This one was our Tarzagi's expression. This one is Tarzagi's expression. So simply this Hansen, Mayer, Vesic, and Mayoff, they simply added some more factors. They added D factor. D is depth factor. So we have DC in this one, DQ in this one, D gamma in this one. This is depth factor. We also have IC, inclination factor. This inclination factor is for the load. IC, IQ, and I gamma. We also have B factor. B factor is for base. So BC, BQ, and B gamma. And last one is, yes, ground factor, G. So GC, GQ, and G gamma. So just they have added these four factors: depth, inclination, base, and ground. So these four factors are added. And here also that before we have SC and S gamma only. Now they have also added SQ. Simply. So these factors, they are added. Their equations are their equation will be simply given. Before, first of all, we'll check this one. First, we have NC, NQ, and N gamma. So what are these factors? These are bearing capacity factors. So their values are given this. NC and yes, NC and NQ gamma. NC and NQ. These values are same for all three of these methods. And for Mayoff, Vesic, and Hansen, we have same values of NC and NQ. This NC and NQ are same. Just this N gamma is different for these methods. So they have all have different values of N gamma. Just take these values. Second one is shape factors. So shape factors we have SC, SQ, and S gamma. Remember that SQ was not present previously. Zavi's SQ is not present. Only SC and S gamma were present. Now they have also used SQ value. So simply SQ and S gamma value would always be same. And if phi is equal to 0, that means the soil is purely a clay soil. So the value would be 1. And if the soil has angle of internal friction greater than 10, so we'll use this value. What is Kp here? Kp is tan square pi by 2, this thing. So these expression would be given. No need to memorize them. So Kp is tan 45 plus pi by 2 and take the whole square of that. So simply put in the values, we can get SQ and S gamma from this. And for any value of phi, we can calculate simply SC from this expression. All right, so this one is K factor. K factors for Mayoff. This one is K factor for Mayoff. For Vesic and Hansen, they are using this formula. So this formula is used. And for strip footing, remember that always take these factors as 1. For strip footing, this shape factor would always be 1. But for strip footing, we assume that L is infinite. The footing is being continued for infinite length. Remember this L is always in the denominator, these shape factors. Here also in the denominator. So we can, if something 1 over infinity is 0, simply shape factors for a strip footing would be 1 in any case. So after this shape factors, we have these depth factors. So again, the same expression, just the difference is this expression D or B. Before we are using B or L, now we are using D or B. D is the depth of footing. After shape factor, we have inclination factors. Inclination factors depend upon the load. For example, if the footing is given like this, and this is the center line of footing, we are saying the load is applied at, for example, 30 degrees to the horizontal. So we have to take this theta is equal to 60 degrees, angle with the vertical. For inclination factors, we have to take always the angle with the vertical. So load with the vertical. We've also shown this here. This is the theta. Angle with the vertical. This is the angle of resultant vertical from vertical. Just remember it is from vertical. So simply put theta here, calculate IC and IQ. Simply put theta here and phi here, calculate IGM. Phi greater than 0 and phi is equal to 0. After these, so we have ground factor and base factors. Yes, these are depth factor for Hansen method. These were depth factor for Madoff, and these are depth factor for Hansen. Hansen and Versick. Versick also has the same. For base and ground factors, those are not in the course. And these base and ground factors, this one, G and B. So ground and base factors, they are not in the course. You can ignore them. Alright, so any issue in this? Simply just we have to calculate these values extra in this one. We have to calculate DC and IC, DQ and IQ, gamma and I gamma, and SQ. So they are extra steps in this question. Simply multiply them and just again do the same. First we find Q ultimate, then Q net ultimate is Q ultimate minus gamma df. If you subtract Q, yes.
Brother, if they given questions from that Hansen method or basic method, these methods, they will provide the equations for the
Yes,
IDC and IC those things.
yes, sir
Okay.
was saying that we have to memorize this general equation, and
Yeah,
we have to
okay.
know what these factors are. What is DC, what is DQ, and what is gamma. Very good.
Okay. Okay. Thank you.
So the steps again the same. First we find Q ultimate, and then we subtract gamma df from this, and we get Q net ultimate. Before we were doing this step directly because we have taken common, but here now we have to do this separately. After net ultimate, Q net safe is simply Q net ultimate divided by factor of safety. That is usually 3. And Q safe is equal to Q net safe plus gamma df. So this is how we can find Q net, Q safe. And if we require area footing, QS is equal to Q total load per area footing. So we can use this effect. Any issue in this? This was all for bearing capacity, and most probably the question would come from this. Usually, sir, I've asked a question. All right, so
Usually numericals will be from these three, one of these three methods, no, brother?
yes,
Hansen,
usually Tarzagi is given because in minutes we do not have time.
Okay. That is a. Thank you.
So afterwards, so most this one bearing capacity is important. Second is this: we have to calculate the string size, just like in PRC2. So this is second important numerical, and third one is this elastic settlement. All right. So if we move towards this one. Solid classification can be asked, but that's a short question, very short. Long question. So if we move to this question, so they are saying we have to design a combined footing. Combined footing means there are 2 or more columns in the same footing. We have given the width, and they have provided that the DF is 3 feet below, or the thickness of footing is 3 feet. Thickness of footing, sorry, DF not. So this is combined footing. They are saying its thickness is 3 feet, and 20 into 20 and 14 into 14 are its dimension. 20 into 20, 14 into 14. These 2 columns. Column 1 load is 300. Column 2 load is 150. This is Q1 is equal to 300 kips. Q2 is equal to 150 kips. and the clear space between them is 11 feet. Clear space. Yes, and Q allowable is 4 KSF, gamma C is allowable is 4 kgs per square feet, and gamma C concrete unit weight is 150 pounds per cubic feet. PCF. So this already is given. This already is given, and they are saying that the loads are net loads. They have provided us allowable bearing capacity, but they're saying that the loads are net load. So simply first we have to calculate net bearing capacity. So net bearing capacity is Q net safe is simply Q allowable or Q safe. Q allowable and Q safe are the same, minus gamma df. So Q safe is 4 KSF minus 0.15 gamma because it is in pounds times this depth of footing. So it is 3. So we can get this 0.45 and 3.55, I think. Yes, 3.55. So we have 3.55 ESF. This is Q net safe. So first we have calculated this Q net safe. Now we know the formula for bearing capacity area. So our area is simply total load over our formula for bearing capacity is total load divided by area. So if we require this area, so total load we have 300 plus 150. 300 plus 150, that is 450 kips divided by is 3.55. 3.55. So this would give us the total area required for by footing. It's 126.76. 126.76 square feet. 50. This is the area. Now they have provided us that the width of the footing is 3 feet. 5 feet. They have already given us the width of footing is 5 feet. So we know that area is equal to B into L. Simply. So we know that B is 5. We require this L. So L is equal to area divided by 5. So that is 25.35. So 25.35 rounded to the multiple of 0.1 to the top upward side. So that would be 25.4. 25.4. Here calculate the L value. If we draw this is the plan view footing. So in footing, if we see that this column is present here, this is present here. Approximately this is 20 by 20 and this is shorter column and it is 14 by 14. Q1 is acting here and Q2 is acting here. And the distance between the columns are, so 11 feet is the clear distance. So if we find this center to center distance, so that would be center to distance. That would be 11 feet plus this was 20 inches, so 20 by 2 plus this one was 14 by 14. This is 20 by 20. 20 inches by 20 inches. This is 14 by 2. Whole divided by 12 because we have to convert this into feet. Simply this is the distance. So if I find this 11 plus 10 plus 7 divided by 2. So that is 12. 12.417. That is 12.42 feet. Simply just find the center to center distance between the two columns. So we know this one. So as these loads are different, this is 300 kips. This is 150 kips. So we know that their resultant would not be exactly in the middle. And if this is a center line of the columns, so the resultant would lie somewhere here. are resultant of these two loads. That is 450 gives. Why it would be towards the higher load side? Resultant would be higher load side. So if we assume this is x dimension, this is the column 1, this is column 2. So if the distance of the resultant from the first column is x direction, so we can find simply x by this by equating moments at point O. Summation moments at column 1. We are summing the moments at this column. Simply, first load is 450 into x. So 50 into x. And the second load is 150 into this distance. This is 12.42. 120 into 12.4 plus is equal to 0. We have these two loads. So simply calculate x from here. X would be minus 120 into 450. So x is, ignore this negative sign because this just shows as the r is not acting downwards, but it's actually this direction. Doing the negative sign, you can find simply the x distance. So they have found the x distance as 4.14. So they are using 4.1 rounded to 10 multiples. You can also round it to 4. X is 4.1. Alright, so we have found this x distance. So if we want to create a uniform pressure underneath the foundation, we have to ensure this resultant acts exactly at L by 2 distance. Distance of resultant from one side of the foundation should exactly be L by 2, and this is L by 2. So for uniform pressure, we know this that we have to calculate. So if we assume this one as XA and this thing as XB, simply just assume these values. So we know that L by 2 that is equal to XA plus X. Right? That this L by 2 is equal to this length. The length of resultant from this side. L by 2, we can find XA from here. That's simply L by 2 minus X, that is equal to XA. We have L as 25.4. Its half would be 12.5 and 12.7. So XA would be 12.7 minus X. X was 4.1. So 12.7 minus 4.1, that is 8.6. Yes, 8.6. The XA value would be 8.6. Simply a value. Yes, 8.6 feet. That's okay. Our XA value is 8.6 feet. And for this XB value, now we know all the distances. Simply XB would be, if I erase this one here from here, the XB would be simply total length minus XA minus this 12.42, the center distance. So we can find XB like this. So that's simply 4 feet. So this is how we have to detail this whole footing. That we know the width is 5 feet, we know the length is 25.4, and this is the distances of the column from the ends, the edges of the. Okay, so this was this question. This question, we first found the area, then from area we calculated the length, and from the length we determined how much length would be in how much direction. What would be length on the left hand side, what would be length that is XA, and what would be length on right hand side, it would be XB. Any issue in this?
No, brother. Okay.
Okay. So if we move to this question, so they are saying that column is 5 inches from property line. So that's simply this question. That this is again the same footing. Again the same footing. Yes, the difference is they have provided this length now. That this is suppose Q2 load and this is Q1 load. This is for this column is 14 by 14, 20 by 20. So now they have provided this length. The length of column 2 is 5 inches from the property line. We cannot extend our footing beyond the property line. That's a limit. This distance to the center of column would be 5 plus 7 inches. 14 by 2 is 7 inches. 5 plus 7, that is 12 inches, so 1 feet. This clear center to center distance from edge of the footing to center column is 1 feet. This distance we know this is 12.42 feet. Again, so the loads are same. Actually, this was given. This distance was given. So this is this. Yes, and the third thing, because the loads are same. So again, the x value would be same. The x value is where the resultant is acting. So because the loads are same, so our resultant would be acting at the same distance. So x would be 4.1 feet. Again, the same one. So now we do not know its length. We do not know its width. Why? Because its length would change, so its width would also be changed. But the area would remain the same because the soil is remaining the same as well as the loads are remaining the same. The area is simply Q load over Q is net allowable or net save or whichever the bearing capacity is. So load and area, soil is remaining the same, so the area would remain the same, but the dimension would change. Simply, we can calculate this dimension. We know this is 4.1 feet, so we can easily calculate this dimension. So this dimension would be 8.3 feet. So we know simply we can calculate this dimension. Why? Because we know the total length 12.42. We know the distance of x from Q1, that is 4.1. So simply subtract 4.1 from 12.42. So 12 minus 4, 8 and 8.3 or 8.32, but they have rounded off. So simply this length is 8.3. So now we know that at maximum our L by 2 should be 8.3 plus this 1 feet. 8.3 plus 1 feet. Why? Because we do not have any more space in this direction, in right hand side. For our L by 2, our resultant must always lie on the half length of the thing. So this is our L by 2. So L by 2 would be 8.3 plus 1. So L would be 9.3 and 18.6. So this is how we can calculate the length of footing. Now again we know the area of footing from the previous question. The length is 8.4. We know the area is 126.76. The previous one 126.76. So the B is simply area over length. In this case, B value would also be changed, and this value would be the width B value. And they have calculated this at 6.8 feet. Previously it was 5 feet. Now the width has increased. Alright, this was simple one. Now we have another type of footing, strap footing. For example, this is a footing. Strap footing is like this, that we have two columns, like this one, like this one. Instead of providing a whole pad between them, like we were doing before, these two columns, we simply make these two isolated footings connected by a tab beam. One moment. For dead and live loads are two columns. They are connected by strap beam. They are given their dead and live load. So we have designed this by UST method. UST is ultimate design method. UST we are going to use factored loads. These are service loads given. First of all, we are going to calculate this factored load. The factored load for first column would be 1.2 dead plus 1.65. Again the same. For factored load for two column would be 1.2 dead plus 1.65. Simply add them to get the total factored load QU1 plus QU2, and this total service load you have to also find. Why? Because this allowable capacity is given for service capacity. You have to find its ultimate capacity or ultimate bearing capacity also. After finding this service loads and ultimate loads, simply the ultimate bearing capacity would be the ratio of this Q over Q. This is Q ultimate that is factored, and the Q unfactored times Q allowable. So simply multiply the factored load summation of all factored load by Q allowable, get the Q. First we create finding out Q ultimate for first column, for second column, summing them. Q is service live loads, service loads. That simply summation of 320 plus 260 plus 500 plus 400. Simply add them. This we have the ultimate bearing capacity. Okay, after this ultimate bearing capacity, we have calculated this ultimate bearing capacity. You know this column, this one. This is at the edge of the property. If I draw this plan, so if these are two columns like this, first one is like this. This is at the edge of the footing. They are connected like this by a strap D. This strap D. So this column one is at the edge of the footing. So this distance, this x distance would be simply this column size divided by 2. The column size is we have given this column size. Yes, they both the columns are 400 millimeter square. So the 400 by 4, the columns are 400 by 400. 400 by 400. 400 by 400. So this x distance would be simply x is equal to 200 or 0.2 meters. Okay. So just remember this x distance. We have to take this from the edge column or the property column at the property line. That would be simply divided by 2. Column side divided by 2. And for this L1 by 2. L1 is the size of this column. This one is L1. So for this L1, we have to use again the same one. That L1 by 2, that half column size should lie exactly at the center of footing. So that would be x plus e. E is some distance between this x and this L. E we do not know. That E, this E value is unknown. So we have to find this E value. Okay, so we can calculate this L1. We are going to now create table. First value we have to use is E meter, I think. First we have to assume value of E. We are going to assume. So this is unknown. Then from the C value, we can calculate L1 value. We add it with X. So second value is our L1. So that is 2 times X plus C. X is 0.2. 0.2 plus C. X. L1 is 0.2. After calculating this L1, now we require this S bar distance. So this S bar distance is simply this total 6.2, this distance minus E. We are going to subtract e from the 6.2. Third thing we have to find is s bar is equal to 6.2 minus e. 6.2 is the spacing between center to center spacing between. Why we are going to find this s1? Because if we here, so q1 is acting here, q is acting here, qu1 and qu2 are getting auto. 1 and qu2 are acting here and here. Now we know the resultant of them would be acting somewhere in the middle. This would be r. Or simply we can use this r as we have provided a formula. R is simply 6.2 into 800 by 5. That if you take the loads about this column 0, the same procedure as before, that we are taking the loads about that column 0. Load about this column 0. So this would be qu1 into s bar. Q1 into, sorry, this whole distance, this would be 6.2. That is equal to R1 times this distance. This distance is S bar. This thing. This Q1 times 6.2. This distance. We are taking moments at this point 0. We look at this diagram. We are taking moments at this point 0. This is pose point O. Summation moments at O is equal to 0. So Q1 times 6.2 minus it is in the opposite direction, R1 times S bar is equal to 0. So the R value for R1 is Q1 into 6.2, that is the spacing, over S bar is equal to R1. This is the resultant at first column. So simply for this R1 value, we are requiring this S bar. So we are calculating this S bar value for R1. So the thing is R1 is equal to Q into 6.2, that is the spacing over S bar. So these we are able to this R value.
Brother, we have to take factored Q load or else service Q1.
No, factored always. For this question,
Okay.
we are saying that we have to use USD method.
USD. Okay.
Yes. Simply we can write it QU1, sorry, QU1. So after this, we can find the Q2 as sorry, R2 as this R2. So this R2 would be R2. Simply this R2 would be Q1 plus Q2 minus R1. Simply add this Q1 and Q2 and subtract R1 from it. Simply we can write as Q whatever the ultimate was minus R1. So simply do this one, and yes, this we can find it as R2. So we have calculated this R2. Why we are finding this direction? Because we are going to use them for finding the width of the footings. So B1 is R1 over L. B1 is equal to R1, the direction of first column, or L1 into Q ultimate. And B2 is equal to under root R2 over Q ultimate. Why a different expression for this? Because this is not a square foundation. This is rectangular one, and this is square. For square, we can simply, as B is equal to L, so we can simply take the under root of this. For rectangular one, the L value is different and B is different. So first we calculate this L value from here. Then we calculate spacing, and for this spacing we calculate R1 value. We subtracted the whole loads R1 from the whole loads and calculate the R2 value and use these values to calculate this B1 and B2 value. All right, so this is the basic methodology for this question. We have to find B1 and B2 values actually. So first we are going to assume some value of E. For example, they have taken 1.2 meters. So for E is equal to 1.2 meters, our L value would be 1.2 plus 0.2, 1.4 into 2, that is 2.8 meters. We can calculate S value 6.2 minus 1.2, that is 5 meters. Simply multiply the QU by 6.2 and divide by S bar. So some value would come, that would be 992. 992. And R2 value is 1048. 1048. B1 value we are getting as B1 is the footing width at column 1. B1 footing width at here. B2 is footing width at here. So 2.14 and 2.52. 2.14, 2.52. So if we see these values are very much different, we have to provide a same footing. Whatever the width is here, the width should be remain at same here. So this is B1, this is B2. It should not be different. So we have to perform a trial again. So this is hit and trial method. So we have to assume another value of E. So C is value. This is value is lesser 2.14. This B2 value is greater. So this lesser value means that we have to increase this value. We have to increase this 2.14. And to increase this B value, we have to decrease the length. Right? So if we decrease the length, so length is dependent upon E. So we are going to reduce the value of E. For example, it was 1.2. We are taking this as 0.9. Or we can take it as 1 again. You can do a trial at 1, then you can do it at 0.9. So if I take at 9, so I've calculated these values 2.2, 5.3, 935.8, and 1104.2, 2.57, and 2.58. So now if you check, these values are very close to each other, almost same. So if we are going to round these values, we can simply write for column 1. The B1 value is L1 values are B1 is 2.57 rounded as 2.6 meters. L1 value is 2. And for column 2, because it was square footage, so it's L2 would be same, and that are 5.8. That means 0.6. And now we have same with, that's fine. We have to do this trial again and again until the weights are almost same. There's very little difference. Right? So this is simply, we have to first, if they are saying that you have to USD, then factor the loads. Otherwise, take the loads as those are given. You don't need to factor them. But if they have specifically mentioned that you have to use USD, then factor them. After factoring them, assume some value of E, calculate L1, and that calculate S bar, R1, R2, B1 and B2. And until B1 and B2 are almost same, we have to do trial again and again, assuming different values of B2. And how we have to check that we have to increase the value of E in the next trial or decrease it, that I was saying from this L value, from this P value, is if the B1 value is less than B2. So that means we have to decrease the length. B1 value is lesser, so to increase it, we have to decrease the length. And to decrease the length, we have to reduce E. If the B1 value is greater, we have to increase the length, so it would be reduced. And then we are going to assume 1.3, 1.4 values like that. Is that fine?
Yes, brother.
All right, so this one We have done a trial at 1.0, but these were still a bit different, 2.4 and 5.6. I've done another at 0.9, so that was more accurate. So afterwards, first we dimensioned a combined footing, then that was trap footing. Now we have a trapezoidal footing. What trapezoidal footing is like the same, just quite same as combined footing. For example, this is given, this whole thing. And remember, there are two types of ultimate USD loads for footings. One is 1.2 plus 1.6, the usual that we use, and the other one is 1.4 plus 1.7. But other, if they have not specified, simply use 1.2 plus 1.6. That is more common. So they have used 1.4 and 1.7 here, 1.4 dead plus 1.7 line. So if we are proportioning a trapezoidal footing, they are saying UST, ultimate strength design. So simply we have to calculate the factor loads first, QU1, QU2, add them QU, calculate the service loads and add them, that is Q, calculate the ultimate bearing capacity, that is QU over Q times Q allowable. Q allowable given was 190. Simply take the ratio of QU and Q and multiply with 1.90. So that's how we can find QU. After QU, we have to find, again, do the same thing as in combined footing. So for example, this was our column. They are saying this is the property line. So this is our property line. We can understand that from here. Column size 0.46, 0.46, 0.46, 0.46. And the distance between columns, central distance is 5.48. 5.48 meters. So that's this thing. So if we draw its plan, so its plan would be something like this. We are considering this as trapezoidal footing. This is at the bottom. This is something in the middle. 0.46, 0.46, 6. The distance between them is 5.48 meters. This distance would be from the edge of property line. 0.46 divided by 2, that is 0.23. That's 0.23. So first, again, the same thing. We have to find where the resultant would lie. R. We know Q1, we know QU, QU2, and QU1. We know the effect, ultimate load. Simply take a moment about any column. For example, if we are taking moment about this column, 1 is equal to 0. Summation moment about 1 is equal to 0. So the value would be R into X bar. This is the X bar. This one. From the central column, the resultant is equal to QU2 into 5.48, the spacing between the columns. So X bar would be simply QU2 5.48 divided by resultant. The resultant is simply Q ultimate. This one. Simply add QU1 and QU2. QU1 plus QU2, that is the resultant. So we can find X bar from this value. Alright, so this is the same one. So after X bar, we have to find X dash, that is distance from edge of property line. The distance of resultant from edge of property line, that is X bar. X bar would be 0.23 half column size plus. So simply if we have, so X bar was 2.395. X bar value was 2.95. And if we add 0.8, that would be 2. Right, so simply we are adding half column side to this X bar and we are getting this X dash value. So the The check for trapezoidal is that we have to find L by 2 and L by 3. And our value of x bar should lie between these. That x bar should be less than L by 2 but should be greater than L by 3. The x bar is lying in between these two values. Then we have to go for trapezoidal one. Otherwise, we can provide a rectangle footing like before. If our L by 3 coming was first we have to find the L. What is the L? So this one is 5.48 plus this one is 0.23 half column 0.23. Simply L is 5.48 plus column size. Column size is 0.46. Simply add them, we get this length of 5.94.
Further, on the side of right hand side, after the column, there's some portion left. No, don't we need to add that portion?
This one? No, we have
No, no.
calculate this one.
Yeah.
This one.
Yeah.
No, this one is we are saying that this is the minimum length. The minimum length of column
Minimum.
will be
Okay. Minimum length. Okay.
from
Fine.
this edge of column to this edge. No extension. Just this minimum. Right? Actually, we provide this extension because we cannot leave like that. But this minimum length. Checking whether you provide a trapezoidal footing or not. So calculate L by 2 and L by 3. So L by 2 and L by 3, we are saying that it would lie in this region, and it was actually lying, so that's okay. We have to go for trapezoidal footing. So our L by 2 was this is 5.94 divided by 2, 2.97. Which is greater than 2.625 dash 2 and 1.98. That's lesser than 2. That's okay. So we have to go for trapezoidal footing. So for trapezoidal footing, this is the formula of centroid. Centroid formula is L by 3 due to A plus B, A plus B. We have to memorize this one. So 2 into A plus B. A side is the smaller side. Always. This is A side. Smaller side is A. The larger side is B. Now we are going to portion this footing. That what could be size way, what would be size. So we know the x bar value, we know the L value. This value. X bar 2.625, 0.625, 5.94, 5 by 3 into A plus B, A plus B. We can simplify this. A plus B, A plus B is equal to something. That is our equation 1. We have two unknowns here, A and B. So we need two equations for this. So this is our first equation. The second equation will come from our area. So we know the area of footing would be Q ultimate is load, factored load over area footing. We know this one. We can find simply Q ultimate, area footing from this one. So we have Q ultimate as 5944.9, 5944, and QU was 289. 289. Simply divide them, we can get area of footing. Area of footing was something like we have done it. So simply we can calculate this area of footing directly. Now we know that for trapezium, the area of footing is sum of pedal size. That is sum of pedal side, that is A and B, into the perpendicular distance between them. That is L. The trapezium, the pedal sides are A and B, and the distance between them is L. The simple formula for trapezium is sum of pedal size into B, distance between them. So take this length from this side to here. A over L equal to A plus B into 2. So this is our equation 2. That we have captured this A plus B, that is 2 times A over L. We can simplify these by putting the values and check them. So 6.337. A plus B is equal to 6.337. We can calculate B value from here, 6.337 minus A. This is the B value. Simply put this value in the equation 1. Our equation 1 was 2A plus B or A plus B. So 2A plus 6.337 minus A over A plus 6.337 minus A. Instead of B, we have written this value is equal to this value. This something value was 1.326. 1.326. So simply we can calculate A value from here and put this A value here and we calculate B value. This is how we can know all the dimension of the trapezoidal. All right. So after A and B, our question is finished. Any issue in this? Or the two before that, the combined footing or trap footing? So this one is again the same. Just they have place property line here. So simply we have to calculate the distance from property line. The x bar distance is always from the edge of the footing, from property line. Simply here a bit difference would come that we are adding 0.2. Why? Because before our property line was here, now it is at here. So we are just adding 2 extra from into this. So this is the only difference. The rest of the question is exactly the same. All right, should we move forwards? So afterwards, this one, we have two types of bearing capacity equation based on two types. So we have two types of bearing capacity. First is based on shear failure, and the second is based on settlement. That settlement of the footing is exceeding the allowable settlement. We have two types of these equations, capacity equations. So we do not have to remember this. Just we have to know this how to use this. So this QS, this Q safe, the bearing capacity safe. QS, this is Tank's equation. So this is QS 105 Bn square, 105 Bn square, RW 0.314, 100 plus n square, TRW. So this is the equation of bearing capacity based on SPTN value. SPTN value. That if the number of flows of SPD are given, so we are going to use this equation to find the bearing capacity. So this is the safe bearing capacity. This is for shear. This is the shear. And for settlement, we use these two equations. That first one was this, and the second one was this. This for width less than 1.2 meters. This is for width greater than 1. So these are going to be used. The question can be asked like this: that SPTN value is given as 8. Because the SPTN values for 300 millimeter penetration is 8, and we have to design a footing for this value. That this SPTN value, and again we have given something like depth of footing is supposed something 2 meters. So we have to dimension this beam, footing. That what it would be its B value, what would be its L value. Like that. So for this one, we are going to use both these equations. We are going to perform here failure as well as this one. Settlement. And that fall here. So simply, if we see this, so did not B values. So we are going to perform trials again here. So for example, for first trial for shear. So for shear, we assume some values of B. And B is equal to 1, 1.5, 2, 5, 3, 4, 5, like this. Take some values of B and we calculate the value of QS from this. Simply 0.105 is a factor, B value, we know this one, we assume this one, and is a those RW and RW bar and RW. These are dependent upon water table. So these formulas are given. That RW is 1.05 dA of PF. So dA is the distance from the footing base to the water table, as this is shown. So if we have no water table or water table is at a very great depth, we can take this RWS one simply. If they have not mentioned water table, simply take it as one. And if the water table is below this footing at the depth dB, so we can calculate this RW, R bar W by this formula. And again, if the dB is greater or equal to B, dB value is greater or equal to B, so RW value would be, RW dash value would be 1. We cannot move more than 1, maximum value would be 1. So if they are not mentioned, simply take RW and R bar W as 1. Put in the values, calculate QS. QS for this was, it was P is for 75, 85, 95, 100, 120, something like this. For shear, our bearing capacity would increase with the as our width increases. We again we have to do trials B and, but we have to use this equation now. This Q allowable for settlement. This is for settlement. So if B is less or equal to 1.2 meters, we have to use this equation. QA is equal to 20 and KD. And if B is greater than 1.2 meters, we have to use this equation. So this factor is different. And KD value is simply this. We have written this. It is depth factor and it is 1 plus 0.33 D or B. It cannot be greater than 1.33. Simply put the values here. Again, assume some values of B. We are assuming these values. And find, you can make also column for KD. So KD column, this KD values 1, 3, 3, 1, something. And find QA values. And the trend would be like this. Now we have to find, we have to tell where the shear values would govern and where the settlement value would govern. This is settlement, this is shear. So if we see that from here settlement values are very large, so the governing value would be always the minimum value. So this one would govern, this shear value would govern. But afterwards the settlement values are decreasing, so these settlement values would govern. Something like this one here would govern, and for some last values settlement would govern. We have to mention this. Okay, so this was all lecture 6. Any issue up till now?
Brother, in final part, these equations will be given in exams or we should memorize it?
Which equation?
That equation. Yeah, these are
These one will
like
be given.
okay.
Yes, these one. There are many methods there if you see. So any method would be asked. With this one, Tang was done in the class, but they can also ask another one for this. So we do not need to memorize them, but we just have to know that how to use them. For example, Smirnov is using different factor. They were using 20, now he's using 12. So these are all empirical formulas. So the last one is settlement. So for settlement analysis, we are going to analyze immediate settlement only, and there are three methods. That is this one, Jambu, yes. Jambu, then we have Shimurtman, and the final we have Timoshinku. So these three methods. The Jambu method is for clays. This one is for clay. These one are for sands, spongeless soils. So Jambu one is for clays, and the other two ones are for sands. So the method are simple actually. For example, for Jambu one, simply the formula is this one. It's SC is rigid or elastic settlement, and mu naught mu1 Qn B over E. S is equal to mu naught mu1. These are two factors, and Qn is the net contact pressure at the base of footing. B over ES. ES is the outer velocity of soil. So this Qn value would be given in question. E value would be given. E value we have to memorize this one. That if it is given, that's fine. Otherwise, we have to use this one. It is 300 to 500 times SU. SU is an unconfined compressive, unconfined shear strength. Sorry. SU is unconfined shear strength. So SU is equal to UCS by 2. UCS by 2. Just like before, it is simply C equation. So if UCS value is given, unconfined compressive strength is given, simply divide by 2. Otherwise, SU or CU is given, that's SU or CU means same. Yeah, same thing. Or C, they're all same. So this one is this. Just we have to find mu naught and mu1 values. So if we move to this question. So a foundation 402 meters, and this is uniform contact pressure is 150 km per meter square. UN is given as 150 kilonewton per meter square. Simply they are given. Depth of 1 meter. Okay, we have to draw this profile. A foundation is lying at 1 meter layer. For example, this is a foundation. The depth of foundation is 1 meter. Depth is equal to 1 meter. In a layer, there is 5 meter thick layer below it and 8 meter thick layer below that. This one and this one. So below the foundation, from here we have 5 meters, and this is clay. This has E value something, and after this we have 12 meters. Another clay but different ES values, and rock at the bottom, incompressible layer at the bottom. That is 75 and 40. This one has 40. This one has 75. This is given. Uniform contact pressure is that we have to determine the average immediate settlement. So simply, there are two methods here now. That if the two layers are given like this, we have to find two things here. The first one is we have to find dF by B. Second is H over B. dF by B is simply 1 meter divided by width of footing is 2 meters. So the width of footing would be 2 meters. So 1 by 2, that is 2.5. dF is 1.5. H over B. So remember, EH is always this distance. The distance from the base of footing to incompressible layer. H. H is always the distance from the bottom of footing to incompressible layer. Remember this, that it is, we have to take this from the bottom and it is up till the incompressible layer. So H value would be 5 plus 1 minute. In a depth of layer, clay 5 meter thick. So our H value would be okay, sorry. So 5 meter was from here to here. This was 5 meter. They were saying that the foundation is lying in a layer of clay 5 meter thick. So our first layer was 5 meters thick from the top, not from the bottom foundation. So from the distance from here to here would be 4 meter. We have to subtract this DF value. 5 meter was from the top and 4 meter would be this. So the H value would be, this is 8 meter. So H value would be 4 plus 8. That is 12 or B. B is we have 2. H is 6. After these two values, we have to move to these charts. These will be provided in the paper. So we have df by b as 0.5. This value df by b. So at 0.5 we can move here, here, here. So almost 0.95. At 0.5 values, we can write mu naught is equal to 0.95. This value would give us mu naught. It is written. And for h or b, we get mu 1. So at h or b 6. 1, 2, 3, 4, 5, 6. So almost this. And yes, we have to find L over B also. This was 2 into 4 meters. So L over B would be 4 by 2. L is larger dimension always. So L over B is 2. So for L over B 2, this one, we can calculate this value. So our mu 1 would be almost 0.6, 0.7, 0.8, 0.85. Mu 1 is equal to 0.85. So now we have all the values. Just the remaining one is yes. So now we have two procedures. First one is can take the average of both layers. That simply we know that ES for 4 meters is 40, but for 8 meters is 75. So it would be like this. ES average equal to 4 into 40 plus 8 into 75 divided by total thickness 4 plus 8. So we can take ES average by this. Now simply for settlement, that is mu naught mu1 mu naught mu1 u and b over ES average. Simply mu naught mu1 we know, u and v are given the contact pressure 150, and we know the b value is 2 meters and ES value is here. We put in the values and get this settlement. So they are taken 0.94 and 0.85. That's fine. Issue. A little bit difference can give. We are taken 0.95 and 0.85. So this one was for Cambo. This one was for procedure 1. The second procedure is lengthier one. That in this was our footing. This one was our first clear day. This one was second clear day. The second method, what they are doing, that they are assuming this is sorry, this one. They are first assuming this, that they are calculating the settlement for this one. This is S1 suppose. They are assuming that the hard layer is at this location. There is hard layer at this location. So our H value would be 4 meters. This one, if it was 1 meter, our H1 value would be 4 meters, and B is again same 2 meters, and DF by B would be same. DF by B would be same. So first they are assuming for settlement 1, H1 is equal to 4 meters. So they are calculating S1 from here. That only the upper clear area they are assuming that H1 is 4 meters, and from H or B they are calculating an arrow B is 2. They are calculating mu naught and mu 1. Then they are assuming that from this to this the same layer, clear layer is present. That first this was ES is equal to 40. Now they are assuming for whole 12 meters. This for whole 12 meters. Only the clear layer with ES is equal to 75 was present. So they are calculating its settlement as S2. That from base of footing to the bottom, that only this one present. And the third thing, they are calculating again this settlement from base to this one, but with ES is equal to 75 S3. So just their superposition. So the final settlement would be S would be this S1. This is due to the top clear layer plus S2. This is due to this whole clear layer. But we are adding this one twice. This we are adding twice. So they are subtracting minus S3. So this was extra. We are adding this twice. So this one is more accurate method. So you can try this. It's exactly the same, just we have to perform 3 trials in this. All right, any issue in this Jambu method?
Brother, if in exam it came, which method we should follow? We should follow that first procedure or second one?
So if there is enough time, you can try for second. Otherwise, I don't think that second it would be enough time. The whole paper would be of an hour, and 30%, 30 from 30 marks, 50% would be from payment also. So I don't think this
Yeah,
was
yeah.
our percent. So just this one is fine. But for practice, you can always try this one. So this one was Jambu method. So after this one, we have Timoshenko. So for Timoshenko method, again, it's exactly same. So if this one was Geotech one side, I found these one much more better than those given by that. This one for were from Sarjan Zeb's one. So for Timoshenko, yes. So for Timoshenko, these are the values. This one is the expression. Settlement. This is the total settlement is equal to QB. Again, the same contact pressure into B. This one is the same. This is pressure different minus 1 minus mu square over ES. And here, remember this mu is not a sum factor. This is Poisson's ratio. So this one is Poisson's ratio, mu. And this is I1 plus 1 plus 2 mu into I1 plus 1 minus 2 mu into I2 IF. IF. So this is the equation. I don't know whether it would find it or not, but it is better if you memorize this. I didn't think said something about this. So it's simple if you try to do this question 2 or 3 times. So this is the equation. So for this we have variables Q and B we will be given depending upon the footing base and contact pressure. Mu naught is the Poisson ratio. It would also be given ES, the modulus velocity of solid given, or we can use some empirical relation to calculate this one. I1, I2. These are two factors. We'll go to them later on. IF. IF is the factor, this one, this factor. So we have to calculate IF from this chart. That for this chart, we have to calculate IF. And for I1 and I2, simply use these tables. But for IF, we have to use this chart. So for example, if we move to this some example. So this example where, yes, this example, for example, this example. So we are given Q naught is given, okay, B and L is given, okay, fine, that's okay. So 6 meter they have told us ES is equal to 2.5, and there's clearly at the bottom. So we have to actually, again, this question is same. Either we can take the average of these two clearlets and simply multiply them, or otherwise we can do both separately and then at the end superimpose them both. So simply taking the average for this one, if we see this question. This one is foundation, 1 and 2 meters. This one is a contact pressure. So these are 3 layers. This one for the soil is 0.3. Remember, mu for soil is from 0.3 and 2.5. We can assume any value from the in between for this. 800 and 1200. These are ES values given of soil, different layers of soil. So we have to calculate this values. So first of all, first we have to find, if we look at this chart, we require DL by B and DA by B. This one. So for this chart, if we see that we require first thing is L by B, and the second thing we require is DF by B, depth of foundation by width of foundation. So if we move to this question, so we know that the depth of foundation is 1 meter. DF is equal to 1 meter. Second thing we know is the width of foundation is also 1 meter. Smaller value is width, 1 meter. So DF of B is equal to 1. Second thing is we have to find L over B. So L over B is L is 2, B is 1. So L over B is 2. So if you move to this chart, so L over B is 1 and L over B is 5. If we see the curves, this curve is for L over B 1. This curve is for L over B 5. Remember that Poisson ratio is 0.3 for this person. So for L over B 2, we can simple this create a curve by our own, that we can say that this is for L over B2. This is from our own judgment. We have to interpolate the curves, that for if 5 was that and 1 was that, so what would be for 2? Remember that Poisson ratio for these two are same, 0.3 and 0.3. So for L over B is equal to 2, we can interpolate this curve, and we know the depth or width ratio is 1. So simply move towards that, and we can calculate depth factor I. IEF is equal to almost 0.7. We can take 0.7. All right, so that's how we can calculate point IEF. We can calculate IEF like this. Now the second thing is we have to find this M and N values. So M and N values. So here's this. Yes. Actually, in the question it was written we have to find at the center of the footing. Actually, the question was given that we have to find the center of footing. So if the footing is this, we have to find it at the center. Those IF value that came was for at the corner of footing. So if we have to find the center of footing, we have to divide this footing into 4 parts. That this 1 and 2 footing, this 1 into 2. We have to divide this at 4 parts. So this one becomes 0.5 and 0.5, 1 and 1. So for one other part, our B value would be 0.5 and the L value would be 1. B dash and L dash, you can say. So actually we have to use these values. In the end, we can multiply simply whatever the settlement was for this, we can multiply it by 4. So if you see this, so L over B we can calculate, and N is equal to H over B by 2. Why they have done B by 2? Because we are dividing it into 4 parts. And actually M dash would also have been L dash or B dash. But because It is also divided into two parts. It is also divided into two parts. So those two cancel actually. So if we do this, that would be like 1 over 0.5. So it's again 2. That's fine. So h over b bar. So that's 10. And we calculate depth of b. So our depth is 1 over this again. Now our ratio would be again the same. Our depth ratio would be 2, and we can calculate this value like this. Because df is equal to 1 meter and b is equal to 0.5. So our depth of b ratio, width ratio would be 2. You can say almost 0.6. So this one is IF is equal to 0.6. We can use this and we can calculate I1 and I2 from here. That they're saying that n is equal to h over b, just like we calculated before. M is equal to L over b. So M we have 2 and we have h over b. This was 10, I think. Yes, this was 10. So for 10 and for 2, we can find this is for 10 and for m is equal to 2. This is for m is equal to 2. So we can find the values as I1, I2 this. So simply we have to plug in the values in this expression and we can find this. This is we have to plug in the values and we can find the answer. All right. And remember we have to multiply at the end by 4 because we have divided our putting into 4 parts. So this 4, I think this 4 this 4 is coming because we are divided into putting into 4 parts because we are going to find its settlement at the middle. If they're saying it we have to find its settlement at the corner, then no need to do this because always the settlement comes at the corner of the footing. By dividing into 4 parts, we can determine the footing at the center. All right, so this is the motion code. Last one is Schmertman. So the Schmertman is again similar, but the difference is we have some strain influence factors in this. For example, this is the question. So we have to draw a chart in this. This is our strain influence factors. This is 0.1, 0.2, 0.3, 0.4, 0.5, and so on. I strain influence factors. We'll in a moment we'll come to this. Second thing is footing depth 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This depth below our footing 10. So just remember this thing that for square footing our values would lie between 0.1 and 2b. For squares our values would be 0.1 at the top and 2b at left hand side. For example, if our b was 3 by 3 meters, b was 3 meters, 2b would be 6. 0.1 and 6, these one would be our values. Now we have to join them. To join them, the factor would be I peak, that maximum peak stress. So its value is this. IVP is equal to sigma 0.5 plus 2.5 plus 0.1 and 2 delta Q over sigma dash V naught VP. Sorry. So this is the formula. This delta Q is simply Q net. That is, we find this total Q minus gamma df. So after subtracting gamma df or overburden from our total contact pressure, this gamma df is sigma VP is overburden at depth 2b. That at for square footing. That for square footing are overburden at 2b depth. That would be at b by 2 depth. For square footing are overburden at b by 2 depth. That would be our sigma vp. So if we go to the example, this one was our footing. B was 3 meters. So they have found this is the total contact pressure subtracted from it, and they found this net pressure. This is the net pressure on the footing. So for IVP, simply they have not shown the calculation, but if we calculate this, so simply we can find this IVP, and they have taken this as almost 0.5. This actually comes 0.6 something, I think. I saw this. So it was 0.6 something. So whatever the value of VP was 0.6, it actually lies between 0.6 and 0.7. So at point half B by 2 depth. So our B was 3 meters. So at 1.5 depth, we have to make this point. That this is the point. Simply join them like this one. This is 2B, this is B by 2, and this is 0.1 for square footing. For strip footing, just the difference would be at the top it would point to bottom 4B, and this line would be at B distance. So simply put the values, and now just make the table and calculate this one. Just make this table. Layer thickness, whatever the layer they have provided us in the question. So these layers are provided. Layer 1, 2, 3, 4, 5. Layer thickness is also given. 1, 1.5, 1.5. So layer thickness is given. That's from base of footing to center of layer. For example, this is our footing. This is our footing at 2 meter depth. 2 meter depth. So our layer 1 was of 1 meter. Then it is 1.5 meters. Then again 1 meters. So the depth of footing from to the center of layer, that would be 0.5 meter for the first one. Because to the center of footing it is 0.5. From this one it would be 1 plus 0.75, 2.25, and to this layer it would be for 2.5 plus 0.5, that would be 3 meters. That is how we can calculate this depth from base to the center of footing. QC is simply given. ES we can assume as 2.5 QC, and IZ we have to find this. So this value is 0.5, 2.253. We have to go to this chart and 0.5. Suppose this is 0.5. So move towards here and go to here. So at 0.5, our IZ value is almost 0.3. So if we draw accurately, it would come more near to this value. So this one we can get IZ for first one. The second layer, our depth is 2.25. So at 2.25, we can go this to and check this 0.55. Third layer depth is 3 meter. You can check this, and this is how we can calculate IZ value for all layers. These IZ values are calculated for all layers. Now simply multiply IZ with the thickness and divide by ES. Get this value, summation them, and our formula is actually C1, C2, C3 to delta Q into this thing. Summation summation IZ into delta Z over ES. So delta Q is net over pressure. C1, C2, C3 are factors. Their formulas are directly given here. C1 is this, C2 is this, and this is the formula. Delta Z C1, C2, and IV. This whole summation we calculated. This is whole summation. C3 is also used in the actual slide. C3 is also used. So C3 formula is this. So this is how we interpret. I'll share some it solve problem so you can be more clear. Any issue in this? So this was all. That first one was this solve classification. Second one, playing capacity equations. All these. Then were these are foundations that we have designed foundations, and also we have to check here and settlement failures. And the last one is intermediate settlement from 3 different methods. Any issue or should we end this?
Brother, from these topics, it means from each topic there maybe can come to the exams, or means like totally how much questions will be there as you means predicting.
So totally, if you check the past paper, I think mostly questions are 2 methods are given, 5 marks each. So like the previous one, Jambu method was given and the diagram was drawn. These 2 diagrams were directly drawn in the first question. So that one was I think of 5 or 6 marks. So like this one, they can give 2 questions and 1 from theory, foundation theory, and of course 15 marks from statement part also. Right?
Okay, brother. Thank you.